So this is today. I'm sorry for all of you that could not make it last time, that the recording did not work. Hopefully from now on it should work. We were talking about this mechanization of articulation, formal systems, computability, language, where it all comes from, and these paradigms. We'll of course make a small recap before we continue, but today's main topics should be how computers and architecture started merging together. We'll see some computer-aided design modeling schemata and what's at stake with computer graphics. But just to kind of make a small recap, last time I showed you what a formal system is and what were the expectations of formal systems in the 19th century. I show you Hilberts' program, who kind of had three requirements of formal systems. They should be consistent, completeness, and he also introduced Entscheidungs problem, or decision problem, to say that if we kind of are able to implement all these three features, then formal systems would help us to define kind of the ground of all mathematics and science in a formal way. And then Principia Mathematica was the work which seemed to be most adequate as a formal system to do such a thing. So yeah, I'll show you an example of what consistency and completeness means in terms of this formal system that we were researching, this MU system. But then, as I told you, in 1931, what happened is that Gödel wrote a paper which kind of completely destroyed what Hilbert was trying to achieve. And one of his most important theorems of mathematics, he defined that this consistency and completeness cannot be both achieved in a formal system. He said any system of a certain complexity, for example, in which we can derive arithmetics, essentially will be incomplete. Therefore, there will be true statements that cannot be derived from the axioms. So there will be some truths that we will not be able to prove. Yeah? Therefore, you cannot use a formal system to prove its own consistency. And in this way, he kind of proved in a more general way that there are simply truths that cannot be proven, and every axiomatic system faces this fundamental limit where you cannot go further with formal logic alone. So the Gödel's theorems, they destroy these two first fundamental expectations of formal systems, completeness and consistency, to be achieved at the same time. And then the final blow happened 5 years later with Alan Turing and Alonzo Church, when they proved in their own way that decision problem 2 cannot be solved. So in practically 5 years' time, this whole Hilbert's program was destroyed. And this kind of started also destroying the goal of this logicist paradigm that I introduced you to, that we can base all mathematics on logics. But then something very interesting happened, because, as I told you, and trying to prove that Entscheidungs problem cannot be solved, both Turing and Church defined two concepts, which are called computability and effective calculability, which are the basis of what we know today as a computation. So one of them was universal Turing machine, which Turing devised as a way to prove that Hilbert's problem cannot be solved. He made a hypothetical machine which consists of a certain number of operations it could do. It could read a sign from a square, write a sign to a square. A square is actually laid down on the infinite tape, and then there could be the machine head could, the tape could go left and right, and you can have these basic operations. They would be stored in so-called M configuration, and in M configuration you could use to define the number of states and actions that could compute a particular set of numbers that he called computable numbers. And then he said, yes, these numbers are enumerable. They're kind of infinity, so to say. You can make a correspondence with natural numbers and all computable numbers, but not so with computable sequences. Therefore, this has a certain limitation on its own, but there is unlimited ways of which you can ask the question. And this is how computers evolved. On the other side, I showed you how we can derive the same things in a functional way. So it starts from functions defined as lambda operators, and define, for example, logical operators as functions, which is called lambda calculus. This is another theoretical mode of computation. Yeah? And then I show you that this kind of led to two schools this logicist paradigm kind of derived two schools of thought. One was about control and automation. I showed you automata theory from Neumann, electrical switches and logical functions from Shannon, and cybernetics from Wiener, like control paradigms. On the other side, computation started being explored as a means of creating a language theory. And you have Chomsky here, who tried to make a system of English language based on rules, which are similar to rules like you have in Turing machine or any kind of computational system. And then this kind of went all over the place, especially relevant in computational biology, and Aristide Lindenmayer, who devised a kind of system of cellular growth based on computation. But what most important thing of that was that the forms he created kind of looked natural, looked like trees, looked like plants. So in his book, Algorithmic Beauty of Plants, he showed how you can use computation to derive these crazy forms of trees. But this was a great reduction already, as I showed you. Chomsky first created a reductionist paradigm out of computation, and then Lindenmayer just built upon that. But let's see how computers and how architecture fits into this picture. So my hypothesis is that how we use computers as architects today, it's mostly influenced by these two paradigms, this control and automation, and one about language and grammars. And I would like you now to show you some arguments why I might think that this is like that, and some basic concepts and history involved with this computational architecture. For that, I will quickly go to 15th century, which was very important for establishing a profession of an architect. And one of the most prominent people in this respect was Leon Battista Alberti, Renaissance man who is created to have invented or established the architectural profession. So practically what he did is he codified means of design into parallel projection scale drawings. And as you know, these parallel projection scale drawings is something that we still use today. They became a standard of how to encode architectural models. And also, we have scale models. They go back all the way to Roman times, but for a different purpose. And only in Renaissance, they became kind of the actual encoding of the design. You see on the right, Brunelleschi's model for Duomo in 3D. And as we all know today, this two-dimensional graphical and three-dimensional volumetric representation is a standard way of how we encode architectural models today, and they are produced by architects on daily basis all over the world in the similar way. And in the first encounters of architecture and computers, what researchers started doing is kind of medializing this technique of drawing. And this prominent example comes from Ivan Sutherland. He's often acknowledged as the grandfather of interactive computer graphics, graphical user interfaces, and also computer-aided architectural design. And in 1963, he created this program, and not only program, it's called Sketchpad. And this was kind of interactive computer-aided drawing program in 3 dimensions, which also used light pen as an input device and an oscilloscope as an output device, so to display actually the drawing. So what kind of slowly started happening with this move was there was a generic model of space being introduced to our computer screens, and this seemed to kind of settle an unspoken agreement that computer-generated space should somehow mimic our natural intuition of 3-dimensional space. And you can clearly see that by placing a camera within a computer, modeling camera in a computer, and like placing an observer in the screen, practically what's going on. And the major technical challenge to be able to actually do that was how can we model and represent these real world or imaginary objects that we want to design or that we want to represent. And one way to approximate these objects was to model them with kind of idealized geometrical components, for example, lines, curves, surfaces, solids, and then project them on a 2D screen. And what this intention evolved into something which was called in mathematics geometric modeling. And pragmatic counterpart of this geometric modeling is called computer-aided geometric design. So then there are two more important terms that we might need to clarify. One is called computer-aided design. And computer-aided design takes this geometric modeling as an infrastructure and then puts on top of it user-friendly graphical interfaces, and then we can use these interfaces to actually intuitively model geometric objects. And another important term to clarify is computer graphics. So computer graphics also appropriate this computer-aided design as a modeling to create virtual objects, but with primary focus to create a kind of realistic simulation of the real world in the screen. And now the goal is to investigate how these ideas behind computer graphics and computer-aided design, how did they influence us? How did they influence the way we think about modeling? Because today, you want it or not, you have an idea of what modeling is. And I would like to show you how did this emerge, and maybe how we can change this path in this way of thinking that we have about modeling. So we will start with this mathematical basis of geometric modeling. And if we go back to Euclid, his geometry, when he describes how he devises geometrical constructions in his book, he uses mostly straight lines and circles. Yeah? And the interesting thing in relation to that is in the 17th century, you had René Descartes. He creates and uses the same elements as Euclid, but he represents them with numbers. And you could, of course, do that with linear equations. For example, y equals k times x. So you have x coordinate and y coordinate, and then you have, for example, this equation. If you say y equals 2x, and you have x and y plane, this was practically what Descartes did. Then you have a pair of points, x and y. These are dependent variables or inputs, independent variables or inputs. So if you put x 0, 1, 2, then y will be twice as much. So 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4. So for 0 we have 0, for 1 we have 2, for 2 we have 4. And then we have a line, yeah, which is completely described by this equation here, for example. Or if we say y equals 0, or y equals 5, then this would be a horizontal line, for example. So with numbers we can kind of represent it. But the question was how to represent curves. And what Descartes showed is that for this kind of algebraic analytic geometry here, if we want to capture circularity, also curvature, then these algebraic elements here, x and y, must be raised to a power. So they cannot stay like this. They need to be squared or cubed or whatever. And the elements which provide us with this are called polynomials. These are the things over there. And polynomial is an expression that sums several algebraic terms that all contain different powers of the variables. As you can see, it's a sum of polynomial terms. You can see polynomial terms over there. So you have a certain coefficient, then you have a variable x, and then it's raised to a power, 1, 2, 3, or whatever. And what is not a polynomial is if you raise it to a negative power. So you cannot raise it to a negative power. It needs to be positive. So they're kind of very simple things. Yeah? But the thing is, what happens if we try to graph them? The idea is that we get curves. And the one important aspect of the polynomial is called degree of the polynomial. And this is the highest term that you have. For example, highest term here is 3, because 3 is the highest power on which we raise our unknown. Yeah? Depending on what is the kind of highest power, we will call these polynomials, they have special names. So if we have first degree polynomial, which means only x, or which is the same as x to the first power, yeah, this would be called a linear polynomial. If you raise it to a second power, this is called quadratic polynomial. If you raise it to a third power, it's called cubic, and fourth degree is quadric, and so on. And also we can define them as a form of a function. Yeah, just like we have y equals 2 of x, we can make this function p of t, where t is a variable. This is also can be represented as f of x. Yeah, So P of t equals a times 0 plus a1 to the t plus a2 to the t squared, and so on, depending on what's the power and depending on these coefficients. Yeah. So you plug the t, and you get some value. Yeah. Now, to go a little bit on a more abstract level, but not too abstract, what is also interesting is these polynomials and vectors, they're quite similar. So we can also add them, multiply them with a scalar and constant. And the interesting thing is, because with vectors you can represent space, you can also represent space with polynomials. So in mathematics we would say that polynomials form a linear space. And there is a mapping from this polynomial space to the vector space. For example, look at the first term. Polynomial of the degree n, so this means, for example, polynomial which has the highest term, for example, n, can be correspond to a vector which has the dimensions more than n. For example, if you have three dimensional, for example, in the second line, if you have second degree polynomial, this can be also represented as three-dimensional vector. So, for example, if we have second degree polynomial in the third row, this can be represented a vector of 3 dimensions, which are represented on the right. And as you can see, they are polynomial coefficients. And what they are multiplied with, this 1t and t squared, as you can see there, you say a0 plus a1 times t plus a2 times t2. a0 is multiplied by 1, because everything multiplied by 1 is the same as this thing. The second one is multiplied by 2, and the third time is multiplied by t squared. So we can just, take them apart. Take a0, a1, and a2, put it in this matrix as a vector, and take this 1t and t squared and put it as a basis. So this is something which we always multiply polynomials with. So the idea is then if you have a polynomial, which can be, for example, a cubic or a curve, whatever curve, this curve is multiplying this basis on the bottom, with certain coefficients. And these coefficients can be represented in a 3-dimensional space. Okay, enough of theory. What are these things good for? So, important thing about that polynomials were used for was, for example, interpolation. So what it means to interpolate. So in mathematics, to interpolate is to estimate values between given known values. So, for example, you have a set of points, those red dots over there, and you would like to fit a curve through them. So why? Because then, although you do not have, you only have values of the red points, then you can maybe assume what is in between 2 points. What is the value in between 2 points? And this is what interpolation was used for. So then if we have, as I told you, if we have n points, then our polynomial should be n minus 1 degree. For example, if we have 2 points, then we need first degree polynomial, which is a line. If we have 3 points, then we have a second degree polynomial, which is a quadratic or a parabola. If we have, like here, 11 points, we need a 10th degree polynomial, which would be, which would start or end with a times x to the 10th power, yeah? To represent that, to represent this curvature, yeah? So then we just, how to find the polynomial which would interpolate this becomes a linear algebra problem, yeah? But when was this possible? So this was for the first time possible at the end of 18th century. An Italian mathematician, Lagrange, he introduced a special form of polynomial that can approximate these given points. And this is called Lagrange form of polynomials. And this was, of course, a great achievement. But over time, it became obvious that if you use polynomials, if you use this interpolation to approximate a set of points, this can often lead to very, very unpredictable results. And why is that? Because polynomial must go through all the points. So if these are all points in x direction, this is y, for example, then our polynomial would really need to go through all of these points. And sometimes this works, but sometimes imagine now that there's a point here. What can happen in practice is that this polynomial can really change a lot of its shape in order to get through this polynomial. So it can maybe go very far. So it could really miss because of how data is distributed. This line might become very weird in order to go through all these points. Yeah. So if data is scattered and not so precise, like usually it is in the world, then this approximation becomes very inaccurate. But then there was another approach to the problem of interpolation, and it's called regression. So now the idea is to find a curve that approximates a set of points, but the line itself does not go through the points. It's kind of an abstraction of the points. It describes a collection of points. Yeah? So now we give up the requirement that we need to go directly to a point, but we try to make this approximation as good as possible for a whole set of points. Yeah? But mathematically, in order to do that, we cannot do it globally, like we did with Lagrange polynomials. So what we need to do is we need to restrict this approximation to an interval. As you can see there, this function is defined on the interval from 0 to 0.8. So it always needs to be restricted numerically. Yeah? So now what you can do is you have this set of measurements, and then for any x, you can just make a horizontal, vertical line and predict what would be the y value, even though you do not have that data point. You can predict with it. And another important application was to approximate continuous functions. For example, let's say that this is a function of x and y. Yeah, this is x and y, and this is a function. Whatever it is, this is some kind of function. And we want to find a polynomial to represent it somehow. So we want to fit a curve in a polynomial. But then you can ask, why a polynomial? Why don't we just describe this curve? Because sometimes this curve cannot be described. And also polynomials are very easy to work with. So this was a kind of interesting idea. Yeah. So what happened in the 1920, a Russian mathematician, Sergei Bernstein, he introduced a method which made this possible. And this is called the Bernstein polynomial. And here you can see this Bernstein polynomial approximating the function. And you can see the number somewhere, n. You see n growing from 160 now. This is the degree of polynomial. So before I show you 10 degree for this curve. And now you see n grows very much in order to approximate this curve. So to achieve good approximation, you need to have really, really, really high polynomial term there. And imagine now trying to calculate 400-degree polynomial manually. It's impossible. It was really impossible to work with such polynomials. Therefore, this became a very interesting theoretical idea that you can do this. But in practice, this was kind of useless. You cannot really do that. Yeah. But what happened later is that people started saying, okay, maybe this doesn't work, but maybe I can use this Bernstein polynomial form to actually create an arbitrary polynomials. So I reverse it. I do not have a function to approximate, but I say my function needs to fit to some, I will choose the coefficients of my polynomial in order to get some kind of curve that I like. So it's kind of reversing it. Started using it for design, but I will explain that later. But let's see first what's the difference between, for example, a graph of a function and a curve. What's the whole idea? And of course, some of these graphs that you see here, they do look like curves, especially if we make, for example, y equals x squared, then this will definitely look like a curve. Yeah? But what's the difference between graphing an equation and a curve? And when you learn mathematics in a school, usually you have this explicit form of a function, like this, y equals f of x, or x equals g of y, whatever. Or you have functions of multiple variables like f of x point y, x comma y equals 0. And then on the bottom, you have a graph of a function y equals sine of x, and you know this sine form. Yeah. So what happens is that you have one variable which is independent, and then y is dependent on x. So y is always dependent on x. So depending on what y is, x is, y will be defined on top of it. And this is called an explicit form of a function. But also there can be a different form of a function. For example, the one on the right. This is how we represent a circle, for example, in unit circle in analytic geometry. So here, there is no direct correspondence between x and y, but it's kind of interdependence of x and y, and this interdependence, so their relation, is equated to a constant, and this constant is equal the radius of a circle. Yeah. So this is called an implicit form, but this does not work well for representing curves. For example, in this way, you can represent a function y equals 5 million x, and then this curve will be very steep. Yeah, for x, y will be way higher, but as you can see the problem, this curve will be very steep, but it can never become vertical. Why? Because this number will need to be infinitely large. Therefore, we cannot represent a vertical line in this way. Also, there are other problems. In functions, always x has only one y, which corresponds to it. Therefore, if our function is like this, for each x, there is a possibility of having two y's. This is not a function anymore. So these kind of curves, you cannot represent. Yeah. So what happened is, when Bernstein defined his polynomial, he defined functions in a different way. So this is called a parametric form of a function. And with all this geometric modeling today, it uses parametric representation. And this parametric representation is a preferred method of representing curves. And it's the only way actually to describe a curve in 3 dimensions. So what happens here is that we separate x and y. We take them apart. They are here dependent on each other. So in this way, for example, y equals 2x, they are dependent on each other. Yeah? If we have x squared plus y squared equals 1, then interpolation, the relation between them is equated with 1. But here, what we do is we separate them. So we separate x and y coordinates. X become a function of t, and y becomes a function of t. Yeah? So we introduce a parameter t and describe x and y independently of t. So for example, if you want to represent a circle now, you do not use this anymore, but you use this. X equals cosine of t, and y equals sine of t. It's a parametric way of representing this. But what happens is, look at the function in the bottom. So now we just say, okay, instead of x equals t, let's say x equals cosine of 3t, and y equals sine of 2t. Yeah? And then take a value t, and take some 0, 1, 0, 2, 0, 3, 0, 4, and just get x and y. Yeah? Calculate x and y. And you start seeing that as I increase this parameter t over time, I started sweeping out a curve. So when t equals 0, this is where the curve starts. And when t equals 1, this is when a curve makes the whole circle, so it's drawn. So as you can see, this t parameter now represents time in which we draw the curve. Yeah? So it's a very different representation. And also, let's say that we wanted to extend this to 3rd dimension. The only thing I need to do is now define z. So let's just say that z equals t. So as t grows, we can also define z to be the same as t. Yeah? So if t is 0, z is 0. If t is 0, 1, z will be also 0, 1. So just by adding that, we get a spatial curve. Yeah? As you can see, it does its movement in x and y, but also does it independently in z. And this is very powerful now, because with this parametric representation, we can kind of control what is the position on our curve. We can control, for example, velocity. If we model things with curves, we can see what's the velocity at any current point. Then there is an order to how you draw a curve. You know what's the start, what's the end. Then you can have easier equations sometimes. And also, you can represent lines independent of this slope of the line. And also, you can completely separately handle x, y, and z coordinates. And these curves that I've showed you, you can have nice results with them. And they are called analytic curves. But they have very limited practical value. And after the Second World War, there was a new interest in these curves, which came with computers. And then the idea was that you can just reverse engineer this thing. Not start with an equation and then draw it and see what does it relate to, but say what curve do you want to have. For example, you want to have a curve of a car. And what you want, you find an equation. So for example, you can define what you want to do. This was the idea, the Second World War. You want to have a kind of curve which you know that it should kind of go to these points. And if you were to bend a stick, if stick was to bend to these points, you will get a smooth curve. So what you want is you want to give points and get an equation of this curve so that you can then interpolate and get all of these points that you can calculate. Yeah? And this was done in the 50s by French engineers Pierre Bézier and Paul de Castellao. I do not know how to pronounce his name. They worked at Citroën in 1950s. And they kind of reverse engineered these Bernstein polynomials, not to approximate functions, but to interpolate curve between points. And this curve became known as Bézier curve. And this whole family of curves became known as splines. Yeah? So the idea is you define 3-4 points, and then you get a smooth curve between them. Yeah? So I want to show you now how we can do this from scratch. So that you know what a Bézier curve is, and you can really define it from scratch. Yeah? So let's say that we want to fit a point through 2 points, x, a, and b, which have coordinates x1, y1, and b has coordinates xy, x2, y2. Yeah? And of course, you know, for example, if we use classical linear algebra, we will have this formula: y equals y minus y1 equals m times x minus x1, and this m is a slope of a curve. But in a parametric way, if we do this, we would get that equation over there. So x equals x1 plus x2 minus x1 times t, and y equals y1 plus y2 minus y1 times t. So as you can see here, we multiply xy with 1, so to say, and we multiply y1 with y. And this thing we multiply by t. Yeah, okay, let's go one step further actually. We can then rewrite this equation, so that's made it simpler, to get the one on the bottom. So if we just calculate this, so multiply t times x1 minus t2, I don't want to do it here, but it's a simple algebraic manipulation. You can get this: x equals 1 minus t times x1 plus t times x2, and y equals 1 minus t times y1 plus t times y2. So now it's easier to see that here we multiply x1 and y1 always by this, always by 1 minus t, and we multiply x2 and y2 x2 and y2 always by t. And you can see now this represented on the table. You can make a table here, yeah, and say that if we have x and y, so x1, y1, first point, x2, y2, we multiply always x1 and y1, we always multiply them by 1 minus t. And these two other ones, we always multiply them by t. Yeah? So now let's, instead of x, y, and y1, let's take a real coordinate. So point A has coordinates 1 and 2. Point B has coordinates 8 and 5. So if we just take this thing and plug in the numbers, so just take the coordinates and plug them, take this function here and plug the numbers in, you get that thing on the right, x equals 1 minus t times 1 plus at, and so on. And if we solve that, so if we just distribute things, we get the thing on the bottom, x equals 1 plus 7t, and y equals 2 plus 3t. Yeah? And now we just need to have some t's and calculate x and y, and you will see that you get a line. So for t equals 0, you get the start point, and for t equals 1, you get the end point. Yeah? Okay, that was very, very simple. And not so impressive. But now to understand why is Bézier, what he did, we need to see how we get to curvature with this. So to have curvature, you need to interpolate with at least 3 points. So with 2 points, you will always have a line. But to have a curvature, you need at least 3 points, because 3 points will define a smooth line which starts at the first point and then ends at the second point, and at the last point. And how can we construct this also from scratch? So on the top, you see the formula that we used previously. Yeah, we have 3 points, and you have the formula. The problem is, this formula only has 2 coordinates. How do we make a formula that takes 3 coordinates into play? So this one takes x1, y1, and x2, y2. How to introduce third one? Do you have any idea how conceptually we might be doing that? So you have three points, A, B, C, and you have formula that interpolates between 2 lines, between 2 points. How to introduce the third? And thus get the curvature. Anyone has any idea?
A and C as a starting point and B as an approximation point. Then you get like curvature.
I don't know if you meant that, but I'll try to explain what you do. You take A and B and interpolate between them. You get a line, yeah? And then you take B and C, interpolate to get a line, yeah? So you can use the same formula for A and B, then use the same formula for B and C, you get 2 lines. And then in the third one, you approximate not between 2 points, but between 2 lines. Between lines AB and between lines BC. And then the third one will be approximation. So let's just show you how this works. I will name these 3 points 1, 2, and 3. So what you do is you see B1, 2. This means Bernstein, Bézier, in between points 1 and 2. So this is the same formula as here. So you interpolate between 1 and 2. Then in the same way you interpolate between 2 and 3. As you can see, just the numbers are different. And now, to interpolate between 1, 2, and 3, you interpolate between not coordinates, but between lines. As you can see, the third line there saying B1, 2, 3 equals 1 minus t times B1, 2, which is the first line, plus t times B2, 3, which is the second line. So practically you can do that. Instead of B1, 2, you just then put these numbers there, put these symbols there. Between B2, 3, you put the other numbers there. You do some algebraic manipulation, you multiply everything, and finally you get that thing there. B1, 2, 3 equals 1 minus t multiplying the first one, 2 times t times 1 minus t multiplying the second one, and t squared multiplying the third one. Yeah? So if you represent this again in a table, you can see that it's kind of similar to this. So now this was blend of 2 points. Blend between 2 points, which is practically a line. Now you can take the same and say I want to blend between 3 points, x and y. Again, I have x1, and now I have 3 points. This is point 1, point 2. Now I have point 1, x1, y1, point 2, x2, y2, and point 3, x3, y3. But now we multiply it with a different set of things. Here we multiply by 1 minus t squared. Second one we multiply by 2 times t, times 1 minus t, and the third one we multiply by t squared. Yeah. It's a very similar thing. And then if you remember how we used to represent polynomial in a standard form, for example, this 3x squared plus 2x plus 5, you see that each one of them is then has a very typical basis. And the basis is, for example, if you have 3x squared plus x plus 5, first one is t squared, second one is t, and third one is 1. But what changes here is that here, instead of this basis, 1t and t squared, you just use this basis, 1 minus t squared, 2 times t, multiplying 1 minus t and t squared. And what's the difference? Difference is if we have, for example, 3x squared plus 2x plus 5, if we have that as a polynomial in a standard form, these three coefficients here are just some three numbers. They do not mean much. But if we rewrite the same polynomial, but now this polynomial, instead of x squared, multiplies 1 minus t squared, instead of this one multiplies 2 times t, 1 minus t, and instead of the last one, it multiplies t squared, the coefficients, which will be here, a1, x1, x2, and x3, any coefficients that you get here. So if you rewrite this in this way, coefficients that you get will actually be x coordinates of a curve that you want to have. So what you can do now is you can now choose the points in advance, and by doing this, you will get a line. So let me show you how. You have, for example, now three points, concrete points, which I plotted there. We have coordinates. We just take this table here, or the formula, which you have there, and just replace values like before, then solve it for t, and we get these two formulas, x equals minus 2 plus 4t, and the second one is y equals 2 minus 6t plus 6t squared, yeah? We get this. This is parametric formula of our future line, yeah? Then what you do is you just need to give some values for t. For example, t0 is guaranteed to give you a starting point, t equals 1 will give you the end point, and these values in between, you can just choose some numbers, and you will get, because you have t, you will just calculate x and y independently. And what you get, for these 2 points, you get some points in between, which look kind of smooth, yeah? So you have a kind of parabola, discretized parabola connecting these 2 points. But if I say I want more points of the t, more samples of the t, then I get a smoother curve. Look, I just increase the number of values, number of values for t, and I get a smoother curve. So if you have better resolution, then this is actually what is taken at resolution with computers. If you have better resolution, things look smooth, although they're still made with lines. And now finally, I want to show you what happens with 4 points. The mathematics is still the same as before. You would first interpolate between first 2, second 2, third, and then interpolate between 1 and 3, then 2 and 4, and then finally between these 2 things. So it's the same thing. You just crunch some numbers. And what you get a table, which is not anymore this, but it looks like this. You see, it has 4 points. It would add 1 more. The first basis would be 1 minus 3 to the cube, 3t multiplying 1 minus t squared, 3t squared multiplying 1 minus t, and t cubed. Yeah? And you, again, take these 3 points, put them in this formula, calculate, get the equation, and what you get between 4 points, you get a curve. So for 11 samples of t, you get a kind of interpolation, but not so smooth. But if you sample t, for example, 50 times, then you get a smooth curve. And this is a Bezier curve. If you work in Illustrator or any other program, this is what we use today still. So in 2D drawing, this is still the technology that we use. So you add points in Euclidean geometrical space. Computer does calculation in the background. And what you get curve represented discretely on the screen. but with such a short lines that you believe it's a curve, but it's actually not a curve. Only the equation is kind of ideal. What you get as a rendering is kind of discretized thing. And then how did this developed? This became standard, of course, for 2D drawing. But it was not easy to work with that in 2 dimensions. So researchers created another type of curve, which kind of generalized on top of this, and this was called B-spline. And then B-spline further developed it in rational spline, and this became known as NURBS curve. And this became a kind of standard curve and surface description in computer-aided design. Because unlike Bezier curves, now each point, you do not have only points. Every point also has weights to it, and weights change the curvature. So you can have bigger spectrum of the curves that you can make with it. Yeah. Now the question is, what happens with surfaces? Lines are, of course, very important, but what happens in surfaces? In the same way as we saw with lines, you can, of course, describe a surface in this way. So say that z coordinate is a function of x and y. So, for example, imagine xy plane. XY plane, and then there are pairs of coordinates in XY plane. And imagine that each of these coordinates, now we get a function that changes it in respect to both, and what you can get is a kind of something curved. Imagine putting some sine and cosine here, and then you get some kind of thing. This way of defining surface is called, for example, a terrain surface, because you can model kind of how z changes in respect to x and y. But again, this has problems, like I showed you before with explicit representation of curves. For example, you could not draw a vertical line. And here also you have certain problems. But then you can also do the same as before and make a parametric form. So what you do, you introduce not one parameter, but 2 parameters, u and v, and make both x, y, and z dependent on now u and v. Yeah? And these u and v parameters are part of the surface itself. Like our parameter t, if you remember, we had a curve, and then in parametrically defined curve, t equals 0 would be a start of the curve, and t equals 1 will be the end of the curve. In a parametric surface, u, when u is 0, this is the start of the surface. When u is 1, this is the end of the surface. And in another direction, when v is 0, this is the start of the surface in another direction, and when v is 1, this is the end of the surface in another direction. And I can show you how this looks like. This is parametrically defined surface. As you can see, y's and u's are now on the curve itself. So you can have a coordinate of the point in a curve being described by parameters u and v, which are kind of these horizontal and vertical sections. But also to each of these points, there correspond x, y, and z point in space. Yeah? I don't want to go into detail. It's not even important. Again, you can make a function like this, which would be a kind of analytic surface, but that's not very useful. So what you want to do, you want to add some points in 3D. You want to add these points, and what you want is you want to get an equation of a surface which kind of smoothly connects, goes through these points. And yeah, this was done with a concept called Bezier surface. And Bezier surface is practically also constructed on a set of points. So you give it a points, and then you get a surface which kind of blends in. Yeah. So how to construct this? I don't want to go into mathematics. Not even important. It's practically you control. You instead of interpolating between points, you interpolate between lines in one direction and then lines in another direction. So it's kind of one set of curves, nest one set of curves in one direction, nest another into it another set of curves in another direction, and you get a surface. Okay, and now let's see how was this actually used for modeling. Now you know how. I mean, definitely what you learned now can be used to construct NURBS curve from scratch, like literally from here with a calculator. I can give you points of any Bezier curve. So I wanted to show you that it's not really that difficult and what's actually going on. But now, how did we get from this to actual models? So we learned about curved surfaces, how to derive them, how to represent them mathematically, how can we compute their values. And now, what kind of modeling does this entail? And we are going to explore a couple of these modeling schemata. And they might utilize kind of different notions of space to encode objects, but what is in all of these methods, what is what is the same? The same is that you start in a Euclidean space, you give a set of points or a set of, give a set of points in 3 dimensions, then computer does something maybe in a different notion of space, maybe topological, and what you get at the end, again, is a rendering in a 3D space. So kind of you start in a Euclidean 3-dimensional space and end in a Euclidean 3D space, yeah? And the first thing which developed from these Bezier curves, of course, it's so-called computer drawing. So 2-dimensional mathematical curves. So you give a control points, like these two. And what computer does is creates a polynomial from these points, and then interpolates this polynomial in a certain resolution so that you can get, depending on the resolution, you can get interpretation of this curve. Yeah? You can get these points back. And then these points are connected with lines. And then this looks like a curve. So this is how computer graphics works. And yeah, in this way, what was possible in the first time is that you can kind of intuitively create curves while satisfying certain aesthetic or functional requirements that you have. And practically, what you need to understand that this is very much in line with this cybernetic idea of feedback chains that we spoke about with Norbert Wiener. Because you have fast computers, and you simply start dynamically changing these curves, removing these points, and instantly the curve changes in a kind of predictable way. So it's like when Wiener speaks about patients with ataxia. You know, brain simultaneously monitors and influences the movement of the hand. So it's not like giving instructions to the hand, but like at any moment there is a feedback loop between your actions and between what your brain senses that is happening. So it's the same here. You start moving this curve. You have fast computers. You move this point here, and before you know it, computer already did this, interpolated curves, created a polynomial, and gave you a new curve. So you kind of learn to work with this, even though this is not natural at all, to give some points, and then the mid one is really not there. I mean, it doesn't go through the mid one. That's the whole point. Mid one kind of stays outside. But you kind of learn to deal with it. It's like you play it like an instrument. So this is what actually happened. But the problem is, by doing that, and you saw the Sutherland with this kind of machine that he used with a light pen creating lines. This kind of modeling, what it actually does, it kind of appropriates this infrastructure of geometrical modeling, but does not reflect on it, does not think anything about it. Simply replace the paper and pencil with these electronic instruments, and do not really touch the modeling itself at all. Just replicate it with code. And in the next step, this, of course, extended to from 2-dimensional to 3-dimensional space, and this is called wireframe modeling. And now you have vertices and edges of an object in 3D, and since there is no volume present here, you kind of need to infer what would the volume be if I know what the lines describing the volume are. So you kind of infer the volume from the lines. The next step is so-called polygonal modeling, and it's a kind of 3-dimensional modeling. And you approximate a 3-dimensional surface by a collection of flat faces. So each of these flat faces used to represent these objects are actually flat. And they are made out of so-called polygons. And the most typical choice for a polygon is a triangle, because whenever you have 3 points, you can make a single plane out of these 3 points. And yeah, these polygons are called polygon meshes. And in case of triangle, they're called triangle meshes. And this is kind of simplest way to approximate a surface. And there are kind of 2 types of what's going on here, 2 types of definitions of a polygonal surface. you have geometrical part. So in geometrical part, you have points, so we call vertices. So 3 points in 3D space. You join them, you get a face, triangular face. And so vertex takes a point in 3D, and this is geometrical description. And then you have topological description, where actually face is defined by 3 points, but it's defined by any 3 points. It doesn't take the geometry. So points contain geometry, geometrical coordinates, but the face does not know about coordinates. Face knows only about points A, B, C. So in one level, A equals 0.2.5, B equals something, C equals something. So this is the level of geometry. And on the level of topology, one face is defined by A, B, C, without taking into consideration what our coordinates are. So this is called topological definition. Yeah? So let's speak about some pros and cons of this thing. We here represent each object explicitly. Each point has a coordinates, and each edge connects 2 points. So therefore, each object, we kind of approximate it. We already know that we are approximating it with flat faces. The problem is you cannot have smooth things like this. So approach to deal with this was engineered by Edwin Catmull and Jim Clark in 1978. They made the most prominent subdivision algorithm, so which kind of tries to subdivide these faces into greater and greater resolution and move them in a certain way, so that in the end you have something, you see the drawing on the right, which really resembles a smooth surface. So you start from kind of sketchy approximation, subdivide, 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 and you get something which looks smooth. Again, yeah, approximation. But then another prominent way of modeling developed in the 60s is called solid modeling, and it's kind of mathematically precise modeling schema. The main point of solid modeling that you can distinguish between what is interior, so what is inside of something, what is outside of something or exterior, and what is the boundary. And this is very important for example, manufacturing applications or construction, because it allows you to compute different properties of a model. For example, you can calculate the volume, you can calculate the area, center of gravity, etc. So because you know what is outside, what is inside, what is a boundary, you can infer these measures. For example, you can calculate how much material will be in the beam. What would be its weight, for example, or in a car part. Or if you have such defined model, you can do physical simulations to determine, for example, internal forces in an element. Yeah. But this solid modeling is not a simple schema. It can be implemented again in different ways. So just let me show for you that you know how this was done. And the simplest schema that was used to model solid objects, it's based on this idea of spatial decomposition. So this is in the simplest implementation of this schema, what you do is you take the representation of three-dimensional space, and you simply subdivide it into discrete elements, and these discrete elements have pre-specified size, and then this becomes a three-dimensional lattice. So you take space, and you practically extend it in all dimensions into a box of cubes. And then you say each of these cubes is, for example, 1 centimeter. Yeah? Subdivide the whole space. So then what you can do then is you can definitely say, because you know the location of each of these cubes, you can say if this cube is full or not. So you can describe it. You can say this is full, this is empty. Yeah? So you kind of get a sketchy representation of an object you see there. But the good thing about this is that you kind of have everything discretized. You do not only can say this is full or empty, you can say the density of this is certain. This part has a certain density. This part has different density. Or this has color like this. This has color like this. Or many other properties you can assign to each element. But the problem with this, of course, it's not smooth. It's not smooth in not a good way. But also it's kind of a lot of redundancy. You need to describe so many things. For example, imagine you have an empty space, but still it's treated like it's potentially full. So you simply have a lot of redundancy. You're describing something which is not there. You describe the emptiness, and therefore you need to compute much more. But when is this thing used? This is, by the way, called spatial occupancy enumeration model, or voxel model. These little cubes are called voxels. This is used when the focus is of modeling is to really precisely characterize each part. And this is mostly used in medical imaging, like, for example, MRI, because you want to know for sure, for example, the density of each part or some of its properties. Of course, then you can use algorithms to smooth it out, but in principle, it's not a very efficient way to model, for example, architecture. Then another way of modeling, also solid modeling, it's a kind of, this resembles kind of a traditional additive subtractive model making. For example, it resembles in a way sculpting. For example, you start removing parts until you are left with, this will be subtractive, removing elements until you are left with your object. Or another way, you start building from simple objects, putting them together like Lego to get something bigger. So you have some kind of basic elements, building blocks, like box, pyramid, cylinder, sphere, and then you create complex shapes through certain functions like addition, subtraction, and so on, union, yeah. And this kind of, you model objects in the same way as you plan to produce them in the future. This is kind of the idea. For example, you can subtract a cylinder from a box, and then you have a box which has a hole in it, you know, stuff like that. And there are three parts to this type of modeling. You have a starting set of primitives, for example, cylinders, pyramids, cubes, etc. Then you have a set operations, and these are those things over there, C union D, B minus C union D, and stuff like that. So they correspond to certain geometrical operations, for example, union and subtraction and stuff like that. And finally, you have this tree structure on the bottom. And this tree structure describes how you start from the primitives and build a more complex object. So it's kind of, it describes a system of creating the model. And finally, you have surface modeling schemata. And the most prominent is called boundary representation. This is what you have, for example, in Rhino and this contemporary programs. So the problem is how to represent a solid by using parametrically defined surfaces. So simplest example would be this cylinder. And how to represent it parametrically. See if I have space. So as you know, cylinder has two circles, and then it has this part which goes around. But to define it parametrically means to define it with a formula so that you can infer each of the points. So somehow you need to take a plane which is unbounded, and you need to define an equation of a circle on it, and to define that these elements are in and these are out. Also, this part which goes around the cylinder, it's also a kind of unlimited plane, but within this parameter space, so-called, you need to define what are the valid inputs. So what are the parts which are inside? And these are defined by these shapes here. Here shape of a circle and here shape of a rectangle. Also, it has two parts of the definition. It has geometric entities like point, line, and surface, and it has so-called topological entities like vertex, edge, and face. Yeah, I don't want to go into detail because these things are not so interesting. I think it's important for you to know them because all of them are used. For example, Rhino uses this. This was early AutoCAD 3D, maybe still doing it for some parts. This, usually it's not used. You do not, as architects, have access to that. This is 3D Max and Blender and all of these things. These are the technology on which it resides, yeah? So if you know how to use this software, then you know what's the kind of modeling behind it. And the last slide is about computer graphics. So again, as I showed you, the first interactions of architecture and computers were through computer graphics. And what I show you so far, and I don't want to go into detail with this, it's not important. If you want to read, you can read it in my book. And there are many books about computer graphics, but I want to tell you kind of the origin, what's the idea and what bothers me about it. And what might bother you also, or not. So I showed you what is geometrical modeling about, and then how this extends to computer-aided modeling. But there's another part, which is computer graphics. And computer graphics always kind of serves as an infrastructure of our computational models. And my argument here is that computer graphics developed as a need to provide a kind of notion of space within computers. But the problem is that computer graphics has really limited itself into Cartesian and this Euclidean paradigm of space. And you remember that we talked about this space, and you remember that we believe that Euclid's postulates are valid because they are true, because they seem to mimic what we see in reality. So because we believe what we see with our eyes, we say they are true. But then later we saw that some of them were actually could not be proved at all. Yeah? So we start defining everything in 3D space and then get rendering in the space. And what happens in the computer, we kind of forget about it. We as an architects, we do not care what computer does for us. Yeah? We just take what, we give it input and take outputs. But for me, there is a very interesting limitation. This limitation really reflects some very fundamental questions of the 19th century that we talked about. As you remember, as I told you, the computer graphics it's about kind of realistically representing space. So it's kind of realistic simulation of the world. As you can see here, how we started and how we ended with these super hyper-realistic renderings. It shows this idea that first you start with faces, with lines, then you add faces, then you add volumes, then you add lights, then you add shading, then you add materials, then you add particle physics, then you add lighting effects, then you add camera effects, then you add VR, and then you are really into simulated reality. It's kind of the path that computer graphics goes to. So we go towards more reality, toward more truthfulness. On the other hand, in the 19th century, what made quantum physics possible and all of this information technology is completely other way of thinking. Is saying that we cannot trust what we see, that there needs to be some kind of other criteria for establishing it, whether something is valid, which is beyond what we can see. This is beyond representation, which is beyond truthfulness. So while in science, in physics, we went from truthfulness towards something else. For example, quantum physics, you definitely cannot see it happening with your own eyes. You cannot explain it in a space-time. It's really complicated and it doesn't make sense. So this is what happens on one side. On another side, with computer graphics and with architecture, we go back to the time before 19th century to represent things realistically, which is kind of the opposite tendency, which is very weird. So we as architects, we do not have an abstraction enough to make this jump that 19th century did. But we go towards more realism. And this, for me, is a very, very strange thing. So we kind of use computers, which are quantum devices, in a way, and we use them to emulate pre-19th century Euclidean worldview. World which is truthful to our experiences. And what we do is practically we just virtualize what we already know how to do, and we just put it in a box, in a computer. And then in order for this to work, we of course need some sophisticated mathematics and engineering, but we ignore it, we ignore how it is being done, and we just reproduce what we already know. So we just take the inputs and the outputs, and we play with them in the same way as we always played, and completely ignore everything which goes in between, which is advanced. And then we reproduce what we make truthfully on our screens. And I think that's the reason why we as architects are very much stuck with this, in the same kind of process of modeling with these tools, because we cannot do anything else but reproduce what we already know. And the next time, I want to show you then what happens when computation entered the design process, when this, which we cannot see in the middle, starts being done by the architects themselves. And how does this influence architecture? But unfortunately, I will also show you the limitation of that, because architects, when they started challenging this middle part, this one which happens in the computer, they again started reproducing the schemas of Wiener and schemas of Chomsky, unfortunately. But there's another way around, which we will talk later. So next time I will show you what happens with computation. So yeah, I was maybe a little bit too fast today. I already finished, which is not bad. So if you have some questions, or if you want me to tell something twice, or if you want more details about something, maybe it's good time now.
Maybe we could have a break in the middle. So it's very hard to comprehend all these things you say.
Mm-hmm.
And then if we could discuss a general suggestion of, I don't know if the others feel the same way.
Sure, no problem.
But it's great, but...
No problem. Okay, let's make a 5 minutes break. We can maybe stop the recording. And then, yeah, let's talk.
I don't mean now, I mean for the next lectures.
Uh-huh.
Just you talk 40 minutes, and then we make 5 minutes doing something.
Ah, okay. Sure.
But not now.
No, but you need to, yeah, so the thing is, you know, I speak here and I'm talking here and I'll, you know, I get excited or I want to finish with it. And if you do not stop me, I will not stop. So please feel free to just stop me. Hey, like, explain this again or make a break or, yeah, of course, just do that. I'm here for you, not the other way around. So, if you have questions, yeah?
So, I wasn't here in the last lecture, but Gödel disproved this one guy, I forgot his name, but yeah. Gödel would also disprove the Euclidean geometry, like that you cannot, it only works because you have these two, that it will prove itself. Am I right? Like,
I mean, Gödel did not disprove geometry.
But he disproved the theorem of it, that it worked.
No, he disproved that you can use a formal system in order to prove that this system is itself correct. So system cannot reproduce whether, it cannot tell about itself whether it's correct. This is something that you cannot do. You cannot make a formal system of rules and system of kind of which follows some certain procedures and expect from that system to be able to prove that it's correct. So this is something that is impossible to do. So if you want to, for example, then if you want to make a system for logics, you cannot prove that it's valid within that same system. You cannot ever do it from inside. You need to do it from the outside. As we show, when we make, I made a last class, I made this example with a formal system of trying to reproduce certain symbols, trying to start with I and starting to end up with mu. And in such a system, what Gödel proved is that there will be some valid strings that you will not be able to prove how you got there. So that practically in every formalized system of knowledge, there will be truths which are unprovable. So either you can prove all the strings, but then the system is not complete, then the system is not consistent, so system is invalid, but you can prove all the things, or it's the other way around. System is valid, but there are things that you cannot prove. And he found that this is a limitation of every formal system. And as we know, formal systems are, for example, what we use in axiomatic definitions in mathematics, for example. How we prove, for example, theorems, or also how we prove anything in logic, also in argumentation.
And also the Euclidean geometry was proved like that.
It was proven that the fifth postulate of Euclid cannot be proven. But yeah, this is not directly Gödel. Gödel kind of showed the fundamental limitation.
Okay.
If Gödel did something to Euclidean geometry, then this is something that I do not know. So maybe you're telling me something that I should actually take a look.
I just read your
Ah, okay.
I don't understand this last slide. This is like the evolution, right, to a perfect simulation.
Mm-hmm.
And you said we still use this 19th century worldview
Mm-hmm.
to do with sophisticated mathematics to do our modeling.
Mm-hmm.
So what should be the goal in modeling? How should we use it?
Well, I think that's the question, actually. I think, but you cannot ask that question until you explicitly see that you cannot go further with this line. So I think that's the whole point of these classes, is sometimes you just do not know what to do. Not because you do not know what to do, but because you do not know what limits you. Then when you see, this is maybe the paradigm I need to, and then you can ask that question. So there is no right, I do not have an answer here for you how you should do it, but I'm showing you what's the limit of what we are currently doing. And of course, in the last years, I can see more people not using realistic renderings at the end, you know. I see it less and less, which is kind of a good indicator. But at one moment, like everything you see on these architects' websites is like super realistic stuff, which kind of should convince you that this is the truth. This is how it should be. And this is really silly to do in the time, you know, 100 years after, more than 100 years after we saw that's a dead end. You see, conceptually there is something wrong with that. Not technically. So I do not have the right answer, but I will show you later what I did and how my approach challenges this. But of course, this is only my approach. It doesn't have to be yours. It's up to you to think about what it is for you. But what is, I think, the promise here is that you as architects who are able to ask good questions, with these questions that you have, you will be able to make your own idea of what architecture should be for you. And this will be very different than someone else. If you don't have the right questions in your tool set, I think then you cannot make a distinction between yourself and someone else. So you just need a question and then everything unfolds.
I didn't get the point about the scale drawings and scale models of the 15th century. Why you said that it was a standard for how we encode today?
Standard way of encoding, because parallel projection is obviously, it's not how we see the world, yeah? We see it in perspective. But the abstraction that, because if we put it to be parallel, then we can preserve distances and angles, and you can take the drawing and take it to the other part of the world and build it. So you as an architect, you don't have to care. You have a way of encoding it, and then this is preserved wherever you take it. As long as someone knows how to read that, this person can build a thing. And this is what architects then become, because it kind of building and the design became kind of a little bit separate. Before that, they were kind of the same. But then the problem was you could not tell to workers what to do, because how do you explain to them? But imagine parallel projection. So now we take this room and we put it in we make rays in a parallel plane. This is, imagine to do that in 15th century. People did not understand why is this good for, or how does this work, because we actually do not see like that. So why would you draw it like that? But then when you think about it, it's actually quite amazing what you're able to do with parallel projections. Yeah, that was my idea. But the thing is that this codified way of describing models, we still use in a way today. We still draw the plans and sections and elevations and all of that. It's a very powerful way of encoding. And today what they try to do with these beams, which is completely nonsense, is they try to say, yeah, the model itself, that's the thing, that's the truth, the geometrical model. So the truthful thing is the thing. And I would say, yeah, maybe there's a better way. And then the beam models are complete, I mean, there is no way of defining, of design. So everything competes in architecture. Everything competes in space. You want to have nice space, but you also need to have electricity running. You also have to have water running. You need to have ventilation. You need to have all of these services integrated, and all of them compete in the same space. And then what you do is you model them geometrically in like beam-like setups. You model them in real space, and then you need to check if the pipe goes into the beam. Because there's no way of knowing. You need to zoom and see if the pipe goes through the beam. And this is crazy in 21st century to model like that. So what you need a different notion of space, because when an electrician designs a building, he does not need a 3D model. He makes a scheme. He says, yeah, this part here, this part here, this part here, this part here. He makes a schema which is topological, which is not geometrical. He calculates everything, takes what the output should be, and gets the calculation. So this thing here, architect would make lines in space and go, crazy things. While how it is really done is topological, in a different notion of space. It's done in a different space. So what I say that we as an architects, we need to know these other forms of space, and then reconcile them, and finally render everything back to geometry. But not make pipes do not draw pipes in 3D. That's crazy. That really makes no sense. That's really a crazy idea. I do not believe how BIM is becoming popular. This is really nonsense. Yeah. So anything else?
I can't understand why the right one is nonsense. It's, for me, a very powerful tool to...
I don't think it's nonsense.
No? Okay, then I
No, I didn't want to say that now I discredit this schema. Of course, it's amazing when you see super realistic thing, but I think what's the problem is that you try to model architecture to this level of realism, because architecture is not only that image. There's so many things about architecture which cannot be represented in that image. So why to insist that this is the final frontier? Architecture is simply not only about the images. And if you use it to make amazing movies, I think it's great. Because you can then the point is not what you see, the point is what story are you telling in this movie. And then this becomes an infrastructure for telling the story, but then the story is important, not only graphics. So also in architecture, I would say that this story is more important than the final rendering. And if we insist on that, then we forget the story. We say, who cares about the story? It looks nice. Yeah, it looks realistic. I would like to have that, I don't care what's the story. So that's my problem. Not the problem. Of course, it's amazing to have that. It's how you use it. What role does it play? So that's the problem. Maybe not even a problem. This is what I see as maybe not so advanced thinking. And then later we will go to quantum physics, and I will show you, what is really state of the art in modeling, and how it's really different from what we do, and really does not depend on seeing things. So you cannot see it. You cannot even explain it with the logic. But it works. And it describes phenomena with great precision. And yeah, it's amazing. And it does not require you to see. And maybe as architects, we can also learn something from that. So that's a hypothesis. Yeah. But yeah, you need takes some time. I have so many things to cover here because it's really not a simple story. But whoever tries to give you a simple story, it's maybe convincing because you can really practice to make it nice and smooth, but it's not a simple story, it's a mess. It's a mess to understand where we stand. It takes really a lot of effort. So that's why I told you it's not going to be so easy, but maybe you get some good questions in the end, and that's most important. Something else? Well, if not, then just the paper is there. You can sign that you were here, and see you next week. Thank you.